Hello and welcome again to another Physical Sciences 3 lecture. We're going to look at Newton's laws of motion today, and this one is on page 33. In the last video, we looked at frictional forces and terminal velocity. So Isaac Newton, I'm going to write in his full name, Isaac Newton developed three laws that describe the motion of objects. We have Newton's first law. An object will remain at rest, so that's, remember, v equals 0, velocity equals 0, or at a constant velocity unless acted upon by an unbalanced force. So it will not accelerate or change direction. Okay, if an object either changes directions or accelerates, then we know that there is an unbalanced, and the key is unbalanced force acting on it. Okay. Newton's second law is it tells us how the acceleration and mass is related to the force, or how the force is related to it. So the size of the force will change the acceleration of that object. So an object's acceleration is directly proportional to the net force on it and inversely proportional to its mass. This is the equation which governs Newton's second law. Okay, so if we give an object with mass m a push, okay, the acceleration is going to be dependent on how hard we push it. That's one example. Okay. Newton's third law: for every force in nature, there is a reaction force that is equal and opposite in size. That's equal in size but opposite in direction. So another way of saying this is for every action, there is an equal and opposite reaction. Okay. And we'll look at some examples to clear that up. Okay, so Newton's first law: an object will remain at rest or at constant velocity unless acted on by an unbalanced force. So in other words, a non-zero net force is required in order to change the direction or speed of an object. Okay, so remember, net force is the sum of all forces. And we've got some examples here. So draw, label, and show the relative magnitude of the forces acting on the following. Okay, so we have a ball at rest on a table. So if we draw in our table, this is our table, and we have a ball, we have the force of gravity, and then because it's not moving down at all, we need a equal and opposite force, and we call that the normal force, and they are equal in size. If a ball has just been dropped, okay, it's accelerating towards the earth, and it's just got the force of gravity acting on it. Okay, you can just do that, and it may have a small air resistance as well, opposing the motion of that ball. Motion of the ball. A ball initially pushed and allowed to roll along a table. Okay, so let's draw in our table surface. This is my surface, and again we've got a ball. Again, we have the force of gravity acting on this ball and a normal force, and they are equal. Okay, and then if the ball is moving that way, then we have a frictional force acting against the motion. Okay. A ball pushed along the table at constant speed. So if it's constant speed, there is no acceleration. So F net equals m times 0, which equals 0. So there's no acceleration. So F net, so that means that all the forces must be balanced. Forces are balanced. Okay, so if we have the same table, oops, and we have our ball, force of gravity is acting on it with the normal force. They are equal. Okay, that's a little bit unfortunate. Okay, but anyway, they are equal forces. This one's a bit annoying. I'm just going to get rid of one of my little lines. There we go. I wanted to get rid of that line. Just to show that they're equal. And then we have, so it's being pushed along this way, F, and that's the push. And then we have our frictional force acting against it. Because they are balanced, they must also be equal. So it's not accelerating at all, but the push must be overcoming the frictional forces exactly the same rate of the friction. Okay, same size as the friction. All right, after a ball has been thrown up into the air, so a ball has been thrown up, so that's the motion. Then we still have gravity, the force of gravity, or the weight force, but we also have now air resistance acting against that motion. Okay, so when the ball was dropped, we were going downwards, and so air resistance was acting against the motion. But this time, the air resistance is acting against the upwards motion of the ball. Okay, a ball attached to a spring and suspended at rest. Okay, so this time we've got some sort of, ceiling or something, and we've got a ball attached to a string. We've got a force of gravity acting on it, and this time we've got a force of tension, or T. That's not very nice gravity. I'll just erase that one. So we've got a tension force acting in the opposite direction of our gravitational force. So these must also be equal. So it's at rest, so they're suspended. It's not moving, so we've got gravitational force and we've got our tension force. I'll just write that in full: tension. Tension in the string, holding that ball up. I have two more examples here. If a ball is lifted at a constant speed, okay, so if we have a ball on a platform, let's say we have a ball and it's on a platform and it's being lifted at a constant speed, then we have force of gravity acting on it. Constant speed means that all the forces are balanced, so it means that the lift is exactly the same. We have a lift force going up at exactly the same rate as gravity. Okay, it's just being lifted at the same rate because the actual ball is being moved up. It's the same as because it's constant speed. Constant speed. Remember, F equals ma. So that means that the net force, I should say, F net is equal to ma. So m is equal to 0. So that means the net force is equal to 0. So there's balanced forces all through there. Balanced forces. Okay, so it's just like our normal force in a way. Just overcoming gravity to be moved at that constant speed. Okay, so, and this is assuming that air resistance is negligible as well. If there's air resistance, then this lift speed needs to overcome the air resistance as well as the gravitational forces. A ball attached to a string and lifted at increasing speed. Again, so we've got a ball and a string, and we've got the gravitational forces, Fg, and then we've got the string, so Ft, and again it must be equal. and I should be drawing them in as equal, but they must equal each other, because again, it's increasing ball attached to a string and lifted at an increasing speed. Oh no, what I was doing, I was saying it's constant speed. If it's an increasing speed, this is why I need to read your questions properly. Let me redraw that again. Oh, we all make mistakes. Here we go. So if we have a ball that's increasing, so that word is important. So it's increasing, so it's getting larger. So it's getting faster. We have our force of gravity acting on it, and then we have the tension force, and it's much larger. Okay, Ft is much larger than gravity. So let's just emphasize that the tension force is much larger than Fg, because the ball is accelerating. Okay, if it's increasing speed, it means that it is accelerating, and it means that there are unbalanced forces. Okay. Alright, so we'll look at the second example in the next video.